Welcome back, students. During our previous classes, that is this one, we have studied about the applications of Gauss's law. During the applications of Gauss's law, we have studied about uh, to calculate electric flux in case of a closed surface, that is a sphere. Then we have calculated irregular surface, and then we have next calculated in case of spherical surface inside a charged surface, spherical surface, and then we have calculated electric flux on a charged surface, and then uh, we proceeded to the next one. That is, this time we are going to calculate, and then before this we have calculated electric field intensity, electric flux due to infinite charge sheet. We have calculated electric intensity by applying Gauss's law. Now another application of the Gauss's law. This one is the last application of Gauss's law, which we will study during this course of uh, study. So it is electric field intensity between two oppositely charged plates. So basically in this class, we will study how we will learn how the electric field intensity is calculated in case of two oppositely charged plates. So if you look at, we will see during the next slide the figure. Consider two oppositely charged parallel plates. The charge densities of these metal plates are plus sigma, that is due to positive charge, and minus sigma, that is due to negative charges, because these are the two oppositely charged plates. So these plates are assumed to be of finite length in order to avoid fringing field. So we have already studied about fringing field, but what it is. It is the case when we move away from the center of the plates or the parallel plates or anywhere else, then the electric lines of forces, separation between the electric lines of forces increases, which results in weakening of electric field. So that's why that type of the field is called fringing field. At the ends, it happens at the end of the conductor. In order to find the electric intensity E at a point P between the plates, consider a Gaussian surface in the form of a box. And why we consider a box? Already plates are there. What's the purpose of creating a box? Because unless and until we consider a closed surface, these plates are not basically closed surface. We can't apply Gauss's law. To apply Gauss's law, we have to consider a closed surface. So that's why a box is taken. Let at point A, a cross-sectional area of the box, as the upper surface of the box is in the metal surface. These all points we have already discussed. So if you have understood or revised it, it will be more easier for you people to understand this topic, to understand how to calculate electric intensity between two oppositely charged plates. If you look at the back side, you have already learned the methods, techniques, how to calculate electric flux in case of a closed surface. Now, this is basically a box in which the metal surface where E is electric intensity, E is zero. Therefore, why it is zero inside a metal surface, we have already discussed. So again, I'm repeating. Whenever you take any type of metal and you place this metal inside a electric field, where there are positive, uh, where there are charges, these charges will apply. These charges have electric field. This electric field is applied on the charges inside the conductor. These charges move to the surface of the conductor. With the motion of the charges move to the surface, there are no charges inside the conductor. They are mostly at the surface. So that's why inside conductor there is no electric intensity. Electric intensity is zero inside any conductor. So this was a logical answer. Therefore, on the upper side of the box is zero. No flux passes. I will explain again by using the figure. First of all, if you want to note on these points, it will be easier for you during the course of your revision, so that it becomes easier and helpful for you people when you are revising it. No flux passes through the sides of the Gaussian box because sides are parallel to the electric lines of the forces. Electric field, I'll let you know how the sides are parallel to the electric field during the next slide where I will show you the picture of the figure. Electric flux at the lower surface of the box is 2EA. Why it is 2EA and why it is 0 to the other side? So here he has calculated by using the basic concept of electric flux through the surface and the angle between E and A. Depending on the angle between 2A, angle between E and A, these surfaces are not having any type of the flux, but only this one is the flux value of the flux which is calculated electric flux in case of two oppositely charged plates, parallel plates. Now first I will discuss the figure, then we will apply it. Look at this one. If you look this one, this figure, it is this portion is talking about, we have talked about this portion which is inside conductor. A portion which is inside conductor, there will be no electric field intensity. Why? Because these charges which are at the outside, they are applying some forces inside these metal, and these charges are attracted by the electric fields of these charges. So that's why at the center or inner side of the metal, there will be no charges available. So that's why electric field intensity along this box is zero, this side. So if you look at, I hope this one is clear. If you look at the other side, this one, as well as this one, if you look at this surface is basically, these are basically electric lines of forces. These are electric lines of forces. And these electric lines of forces have some direction because these are the vectors. These are the vectors. So they are having direction along this one, that is positive to negative side. So this is the basically direction if you look at. Now, what is happening here? Again, you come back and you see that this portion is inside the metal where there is no electric field intensity. And in this case, the side of this box, this one, is basically parallel to the electric lines of forces. But the amount of the portion of the area which is your under your study, that is this one. I'm taking it outside. This one is basically area, and the direction is a direction of area is this one. Again, if you see to the other side, this one is basically direction of the area, which is not parallel actually, because I have discussed during my previous classes that if you want to understand, you have to see there two, you have to find out the difference between the two. This is the side of this box. This is the side of the which box which you have taken as a closed surface to understand, to calculate, to apply Gauss's law. Otherwise, you can't apply Gauss's law if the surface is not closed. So you have taken this box. So for this box, this side, this area, that is del A. This area is perpendicular to the electric lines of forces, that is E. If you look at these are the values of E. This area is perpendicular to the electric lines of forces. Again, the same is happening here to your right side. This one is A and this one is E, which is these two are perpendicular to each other. But if you look at the surface, that is of course looks parallel, but we are concerned with the area and the electric flux and the electric intensity. To calculate electric flux, we need to know what's the value of angle between area, which you have considered, and the electric lines of forces. If you come back at the lower side, this one, this face, if you look at this face, you are taking area this one, and this area is basically in this direction at this surface, at this side, and it is this one is the A, and this one is basically E. If you look at this face, at this side, E, this one is E, and the other one is A. Electric intensity area, both are along the same direction. Uh, the portion of the area which you are considering of this closed surface, that is del A, and the electric lines of forces, the direction is this one. If you find the angle between the two, the angle is zero. This shows that there is no electric flux along this side, which is inner side inside the conductor, which I have already discussed. There is no electric flux in case of these sides because the area is perpendicular to electric lines of forces. This area, this one area is perpendicular to electric lines of forces. But in this case, if you look at this area is basically parallel to electric lines of forces. So here it is, there will be electric flux in this case. And you know, these are the charges, and due to charges, there are electric lines of forces, and you will apply Gauss's law. And after application of the Gauss's law, you calculate 1 over epsilon naught q, the charge enclosed within the closed surface, this closed surface, closed shape. So comparing 1 and 2, you are getting EA, that is 1 over epsilon naught multiplied by Q. This is the total amount of charge enclosed by the surface. Due to this charge, these electric lines of forces are passing and through area A. If you look at, you can calculate the charges if you know the surface charge density by using the concept of surface charge density. So these are the charges basically, and it is equal to surface charge density divided by A. If you define from equation 4 the surface charge density, it will be sigma is equal to Q divided by A, number of charges per unit area. Putting the values from equation 3 and 4, we get this one is basically, if you look at this one is basically charge, and this one is area. After putting value, this area is cancelled with this one. Finally, if you are look at 1 over epsilon naught sigma, that is E. So this is the formula to calculate electric intensity in case of two oppositely charged plates. So if you look at E is equal to 1 over epsilon naught sigma n. N is basically a unit vector which shows the direction of these electric lines of forces, in which direction these electric lines of forces are. So this shows the direction, a unit vector which shows the direction of electric lines of forces. So this one. Here, if you look at this one, if you look at this one, then to the opposite side, this unit vector shows the direction. And its direction is along this one. From positive to negative. This unit vector shows the direction of electric lines of forces, in which direction electric lines of forces are moving. And this is the formula to calculate electric intensity in case of two oppositely charged plates. If you look at the gives the electric field between oppositely charged parallel plates, the magnitudes of the field is independent of the position between the plates. It is independent of the position, but it depends on the type of the surface. If you are if you are going to apply Gauss's law, you have to consider a closed surface. Similar, you have steps you have taken it for this one. If you look at this box, you have placed inside two parallel plates where you have one side of the box inside the metallic surface, another one is outside. Here there is no electric field. I have already discussed here the angle between E and A is 90. There will be no electric flux. So this will be the only portion where there is an angle between E and A that is along the same direction, means zero. Here it will be the maximum flux, electric flux. And because we are considering the closed surface and we apply the Gauss's law for the purpose. So when we compare these two, here it comes the concept of surface charge density. And by using the definition of surface charge density, you have calculated the number of charges available in that surface. So that is phi A, sigma A. It is equal to EA. A is cancelled with other A. Then it is 1 over epsilon naught sigma, that is E. This formula is used to calculate electric intensity in case of two oppositely charged parallel plates. So to get the direction of the electric lines of forces or electric field, we use a unit vector which shows the direction. So with this, our class uh, is at end. So I thank you all for your patience. Hope you people have understood it. During next class, we will study about electric potential. This will be our next topic, and get ready or go through once, read it only once time, so that it becomes easier for you to understand what is the concept of electric potential. Again, come back. This was the topic for today, and today we have done about the application, last application of Gauss's law, starting from the first one, irregular surface, regular surface, a charge is fair, upper side surface charge, inside no charges. And then we proceeded for the next one, that is to calculate the electric field intensity in case of infinite charge sheet. And then uh, for the last one, that is to calculate electric field intensity in case of two oppositely charged parallel plates. And we have calculated this one is the basic final formula to calculate electric intensity in case of two charge plates. This is the medium between the two charge plates. This is the surface charge density, and this n shows the direction of electric lines or forces in the field. With this, I thank you all for your patience.